Hello, happy Hanukkah. I'm happy to introduce our speaker today, Oren Ratz from the Weizmann Institute of Science. Oren did his BSc at the Hebrew University, then moved working for his PhD with Nurit Dudovic at the Weizmann Institute as an experimentalist working with fast photonics. Then he switched to theory, going to Chris Yavshinsky at the University of Maryland. And since after his postdoc, he's a faculty member at the Weizmann Institute of Science, associate professor since 2022. And today he's here, well, according to the abstract, to disappoint us with respect to the physical computing. So the stage is yours, please. Thank you for coming.
Thank you very much, and thank you everyone. I'm very glad to be here. So I see some old people in the crowd. You probably all remember, some of you remember analog computers. These used to be big things back in the days, but at some point they disappear, and recently they seem to be back in fashion. So I'll try to sort a few issues regarding that. So we'll start with an appetizer, a lesson from SAG and FAG. Again, the old people probably know these ideas, but I'm not sure everyone. The first dish will be analog computer history and present day. So what's going on in this field? I'll dive into a diabatic computer, which is a specific type of analog computers that are very famous, and you might hear about them here and there. And I'm not sure we'll have time for desserts. If we'll have time, we'll go abstract and try to do some stuff. So let's start with an appetizer, a SAG and FAG. Let's start with the SAG. That's called the spaghetti analog gadget. That's an old idea. As I promised, there would be some quite old ideas around. So the question I try to solve is, suppose I have a list of lengths n, and I want to sort it by the order of the numbers. Okay, and I want to do it as fast as possible. So if I use my computer, which is basically a Turing machine, I guess most of you know that this would take n log n, and this omega just stands to the fact, just represents the fact that you can do much better. You can actually achieve that. So sorting a list of lengths L, according to the computer science definition, takes you an n log n steps, right? And the nice idea is that we can build an analog gadget that sorts at omega of n. And this analog gadget is just this spaghetti rods. So let me try to convince you that using spaghetti rods, you can sort any list at omega of n rather than omega of n log n, right? So that's the first thing you have to do is find the largest number in the list. So you have to sort your list and find the largest number. This would take you at most n steps, right? Actually, exactly n steps. This would be the full spaghetti length. So my longest rod, the long rod would be the longest, the highest number in the list. Okay? The next thing, I will cut the spaghetti rods in the length of each element in the list. So I would map the list into my spaghetti rods. That's again exactly n steps, right? And now I have to sort the list. Any guess of how would I do that? I would slam the rods against the table, choose the highest one by coming from the top and choosing the highest one. Pick it, this would be the longest, the second longest, etc. This would take me another n steps, right? And so the overall complexity, if you have n, you add them, it's omega of n. So with n steps and a set of spaghetti rods, you can sort a list much better than any computer. So what is the lesson from this? So of course this is a joke, right? I don't expect any such machine to compete my device. Yeah, I won't buy this for more than 10 shekels or something. So the first thing.
I'm not sure that's going to work.
Okay.
Why? Because you're sorting the spaghetti. So then each spaghetti, basically, you map the element in your list to the specific spaghetti. But now you've selected the spaghetti, then you need to map it back, so it will take you another
n.
n.
Yeah, so another n would still be O of n. N log n means something that grows larger with, right? N O n is not, okay? So as a physicist, the first thing that you'd say, okay, let me finish the slide and I'll take a few questions. First is complexity is not everything. The fact that the computer science definition of complexity is such, okay, there is a prefactor. In computer science, you don't care at all about this prefactor. It can be huge. In this case, it is huge, right? There is time scale, there is prefactor. There are many things that in computer science you just ignore completely, taking the n to infinity. In practice, you care a lot about. So complexity is not everything, and as a physicist, we should take this into account. The second thing is actually something important that we can take is that analog computer can be better in specific problems. This is better than that in some cases. So you have to identify what is the physical resource that enable you to do that. And in this sense, what is the physical resource here? I would claim this is parallelism. The fact that I can take the longest road at O of 1 rather than O of n, this is exactly where I gain this log n, right? I can find the longest one at just coming from the top and hitting the first time. This is O of 1. So that's why the spaghetti is better than a list in a computer. Yes?
Well, it's not really O of 1 because, like, we say, oh, it's obvious that one is larger, but that's technically because we quickly are able to compare it to all the other ones.
So
if you have
do what I say. Do this and come from the top. This would be a single step regardless of how many rods you have.
Not if you have too many rods to fit in your hand.
Don't put it in your hand, right? Put it in the machine, right? Of course, it's not practical, but in principle, this is right. Also, there is a limit to how much bits I can put in my laptop, right? There is this famous Lloyd's paper on how many bits you can store in a 1 kilogram of a laptop. It's not that much, right? So there is always a limit, but the principle is O of 1, right? That's somewhat a stupid example that we can take a listen that sometimes maybe physics offer us an advantage in computing, right? And so the resource here is just this parallelism. Yes?
Again, I'm not sure that you'll get it because the mapping, you have to have n for each one of them. So
No. Well, I have the list of, right? I have, okay, let's discuss it later on. That's not the main part of the topic, as you can imagine.
I think the main conclusion is correct, regardless of the example. I mean,
So here is another example that's called FAG. That's the Fourier analog gadget. That's less of a joke. Suppose I want to do a Fourier transform. Okay? I can do it with a lens. Right? A lens takes the Fourier plane, one focal plane to the other focal plane. It does a Fourier transform. Now let's try to see what's the complexity in terms of computer science of this, right? So it does a 2D object I can do a Fourier transform of a 2D object by putting the object here, right? Suppose I have an n by n object. Well, it's not that you can imagine that I can build as small as I want and make it as fast as I want. It's not the case because the resolution is limited, right? I have the wavelength. A single point cannot be smaller than the wavelength. And so if I accumulate more and more, I'll have to use more and more points here. And so the distance would grow. And so the complexity, the diffraction limit plus image size plus speed of light get you something which is linear in the total number of speed, right? That's in comparison to 2D Fourier transform, which the best algorithm that we know is n square log square of, right? And O of n and O of n squared, that's already a big difference. And also, it's not as silly as using spaghetti rods. Optics is fast, right? Basically as fast as you can. And so it shows you that sometimes this physical advantage, just the fact that you can do 2D Fourier transform. If you think of a 1D transform, this would be n compared to n log n. It's not really a big difference, but in 2D, it's n squared compared to n. That's a big difference. And what is the computational resource here? Again, parallelism, but in a different sense, in the sense that in computer science, in a computer, the best algorithms that we know of doing a 2D Fourier transform is basically Fourier transforming in one direction and then in the other direction, whereas the lens actually does the two directions simultaneously. So somehow optics does that better than what we can do, and that's not a joke. You can imagine that if you have something that requires doing Fourier transform again and again, many things, this might be a good option. Actually, those old enough to remember the old days of SAR radars, right, the SAR radars, they used optical device to do the Fourier transform to analyze, right, in SAR radars, you take radar picture with the phase and then post-process the information to build the different directions and to get the mapping, to get the accurate mapping. And historically, they used optical devices of this type to exactly do it. So historically, this actually played a role. Right? So that's another example, somewhat trivial example. And actually, this example, of course, these examples are not new, and analog computers have a very rich and interesting history. That's the oldest device we know of that we believe used to be a computer. It's a kind of an astrolabe, what we would call today. It's used for astronomy, for astronomical navigation, to do quick calculation of where do you expect, if this is star in this direction, that star in that direction, what can you say? And basically, such gadgets, such computational gadget, accompanied history, probably the state of the art is something like that. That's a differential analyzer. That's a combination of mechanical device and RLC circuits that was used to solve PDEs. So you put the boundary condition and the PDE by tuning electronics and mechanics and solve the boundary value PDE problem, a set, so not every PDE, but a large set of PDEs were able to solve using this differential analyzer. There were two copies of it, one in MIT and the other in England. And actually, such analog device continued all the way. That's the kind of I will put this as the end of the old part of analog devices. That's a bomb sight for airplanes. It cost basically as much as, so the effort in building this was almost comparable to the effort of a Manhattan Project. It cost almost the same. And this was an analog computer where the people aiming for the target would just have to look at the target, and all the computation would be done analogically somehow within the device, such that the bomb would hit the target. So that's a quite crazy analog computer. From this point on, basically, digital computer took the lead, and hardly any analog computers were used. Yes?
What about Enigma?
That's probably somewhere in between, but it's, I wouldn't necessarily call it an analog. Yeah, I don't think it's an analog device, but right, it's just a simple mapping. It's not necessarily okay. We can.
Yeah. Okay.
Yes.
What about the differential engine?
The
Differential engine.
That's kind of a similar idea to that. As far as I know, at some point, so basically beyond that, no one continued to use these type of machines. At some point, they kind of disappeared. But of course, there is a wake of, a few users here and there. So it looked like at some point a digital computer took over. Why? Mostly noise, right? Mostly noise issues that made these not very efficient, and they were not very versatile. If you want now to solve a different class of ODs or PDE, you have to basically build a new device. Very costly, not very versatile. So one machine can solve one type of problem, and of course noise sets a limit on how good this can be. So historically, these used to be a very important device back in the days, but at some point they seem to disappear. And let's do fast forward for today's. So if you want to know if a subject is a hot subject, you look at Nature Publish Group. And recently, last August, they opened this unconventional computing journal, right? If Nature opens a new journal, probably there is a hype in this direction. And these are the articles that I write. These are the December issues. You can see people are publishing there. So there's definitely a hype about unconventional computing and all kind of analog computer, etc. So it seems like something happened, and at some point, people started to be interested in this alternative to my laptop or to your desktop as a computing device. And the question is why, and is there anything there? Is there really anything there? So I must say, probably I'm ignoring kind of the elephant in the room, which is quantum computing. Definitely quantum computing is there. You can claim that this is kind of unconventional computer. I'm not going to, and yes, it can solve things that we don't know how to solve in the computer. That's not the main focus. I think you probably had enough talks on quantum computers throughout the last few years. I'm not going to cover at all the standard quantum computer, right? That's not the idea. The idea is to check or try to discuss, well, what about other issues? So I think many of the ideas that I'm going to present, or the machines that I'm going to present, started along the line of, quantum computer can do much better than classical. Maybe my system can also be sold as a sort of a computer. And so that's kind of what led, I believe, probably some fraction of the technologies. I'm not going to talk about all of them, but largely we can divide the technologies that are people now using, which are very different from your standard computer, into two classes. The first class is analog computer for solving linear algebra problems and related problems. So these are not difficult problems. Suppose you want to invert a matrix, right? Suppose you want to multiply a matrix by a vector, something like that. There are optical devices. Well, the Fourier kind of hints why this is good, right? There are many, like Classic, the Israeli company Classic, they are trying to advertise a quantum computer not as a real full-stack quantum computer that can crack RSA, but rather as something that can do linear algebra very fast. There is a nice idea by Gavin Crooks, who actually left academia and is doing this in his startup, Normal Computing, on thermodynamic computers, memristor, crossbar arrays. There are several such technologies. And what is the idea there? The idea is not to do something very sophisticated. It's to use other device to do something that used to be something right in up until recently. In multiplying a matrix by a vector was something my computer did very well for everything I need. And then AI came, and the number of times I have to do this linear operation became so huge that if you can spare something either in terms of time, or in many cases it's not about time, it's about energy, then there is a market for that. So here the question is not whether it's possible. This is possible. It is possible to multiply a matrix by a vector optically. The question is, can you do it fast enough and at low enough energetical cost such that this would pay the bill, and for this specific use you'll use something that is not necessarily your silicon device, right? Yes.
So some of the technologies, at least the concept and ideas, are not new.
Yes.
And
It's
so why now?
so again, a lot of it is the need for linear algebra done fast and
But
cheap.
that's not enough. Because
It's-
the need was before, so we need the technology.
I don't think
that
that the need for specific operation done again and again was that it had enough market. I think what really happened here in this area is that the market it became large. That's at
That
least.
I'm not sure.
As you mentioned, so most of these ideas are not new at all.
Yeah, but there is a technology gap.
The technology is now pushed forward, for example, in optical devices, because people believe that, for example, take the heat consumption. It wasn't such a big issue until quite recently. Nowadays, the heat consumption or the energy consumption is a big issue, right? The cost of all these machine learning factories is quite big. I don't think it was that of an issue before that. It's probably a matter of size, but as you mentioned, these ideas are quite old and not new. I'm not going to say a lot about this. Here, the question is mainly whether it's cost effective for the market, because the ideas are quite old. You can do the analysis for each one of them, see that it has some benefit either in energy or in terms of how many computation you can do in a given time. There is a gap there, and the question is, will it be faster than your computer or not necessarily faster? That's a technological question or maybe economical question, and I'm not going to spend a lot about this. There is a different type of analog computers that are more interesting in my perspective. And these are type of machines that claim that they can solve questions that we don't have good classical algorithms to solve, right? So laser solver, light solver, entity research, etc. I think Avi Peer here also did a few of these. The claim, at least of NTT, is that they can solve difficult problems that we don't have good algorithm to solve, like NP-hard problems, right? Light solver, it's interesting, and up until recently, this is what they were doing. Now they back off the claims that they can solve difficult problem, and they are trying to solve PDEs, which is basically the old side, right? D-Wave, which is quantum, but not real quantum, I'll discuss this a lot. Adiabatic annealers, Memrisor computing, bifurcation machine, digital annealers. There is a class of such systems that claim to be able to do something better than anything we can do on a classical computer. And that's interesting. That's already something. Well, is there something to it? That's the main question we want to ask. Yes.
What type of problems are they aimed at solving?
Excellent question. So what do I mean by difficult problem? So I will focus on a specific problem, which is this is what many of these are doing. It comes from physics. It's a Shelton-Kirkpatrick spin glass ground state. So suppose I give you this Hamiltonian, where the Ji's are random. So the most important is that they can be sometime positive, sometime negative, right? And you want to find the ground state of this Hamiltonian. Okay? This is known to be an NP-complete problem. What NP-complete means for us as physicists, again, if someone here is from computer science, I'm sorry, I'm not even going to wave my hand, etc. NP-complete means that for some GIJs, this problem is very hard, in a sense that you can map every other NP hard problem into this. So this is with a polynomial overhead or something like that. So this is this type of problems which came from physics as a spin glass problem is kind of the archetype of what this system does, and for a reason many of the models of physical computing device, including D-Wave, bifurcation machine, digital annealers, OPO, etc., what they actually try to do is to find a ground state of such Hamiltonian. So you have a device you tune the GIJ based on your problem. So you are trying to solve a problem. You map the problem into finding the ground state of this Hamiltonian. So you take this GIJ and somehow map it into your device, and then open the device and hope that it will tell you, that's the ground state, right? So somehow the physics evolution of the system should give you something like, that's the ground state of the system. And the main question is that so? Okay, so there are a few examples. I work mainly on things like OPO. Actually, the system I'm working with is Near-Davidson system, which is more like the XY model, not exactly the same, so I will not discuss it. D-Wave, I'll talk a bit about D-Wave. Bifurcation machines are related to D-Wave, and I'll talk about that. So let me give you an example. Let me dive into the first example, which is D-Wave.
Oren,
Yes.
those four companies that
D-Wave,
Bifurcation-
D-Wave is a company.
Mhm.
Bifurcation machine is Toshiba. Digital emitter is Fujitsu. OPO is NTT. For each such company, each such technology, there is at least one company, sometimes more. The OPO is way more than just a single.
And what is their motivation to why they care about this problem?
So, for example, D-Wave, you can buy for $1,000, you buy half an hour of computing time, in which you can take your GIJ and they provide you, run it for half an hour and get the solution of what's the estimated ground state, right? And they sell it. So some companies that have optimization problems actually buy computing time from D-Wave or from other companies like, as I mentioned, Fujitsu, Toshiba, and they actually pay to get the ground state and use it for their optimization problem. The surprising thing is that usually in this optimization problem, the meaning of this optimization problem is that if you improve it by a bit, you gain so much in the output that paying $1,000 for Toshiba or D-Wave or Fujitsu is negligible. They usually pay all of them. So they all present customers, and the customers usually are the same for all the companies, right?
Why not using Amazon or something like that? I mean, put it on the cloud.
They usually the optimization problem you have, I don't know, you are building a factory, you want to place, I don't know, the air conditioning units, and the exact, if you can save one air conditioning unit, that's about $1 million. So you spend a few $1,000s, you pay for companies that does the computation classically, D-Wave, but you pay all of them, and you take the best
You have the
solution.
money, okay.
Yes.
I'm actually curious, how do you translate locations of air conditioner units?
So it's a
GIJ.
decision. So it's not always the Eisen machine. Sometimes it's actually XY machine. But the idea is that you take a decision, and a decision can be right. You can a decision is like you map it to a spin, and many of these problems can be at the bottom if you translate it into into this ground set of such Hamiltonians. The mapping is not always trivial. But there's a huge factor in computer science of how to map different problems to another.
Yeah, but then you have no distribution of the JIJs. It's a specific.
Good point. Good point. Keep it. Very good point. Yeah, we'll talk about this distribution. That's an excellent point. So it will be important.
There's another point here, no? I mean, the algorithm will be very different from the analog machines. Than the
So here the algorithm is just run the device. Physics should take care of. And let's
So somebody needs to write the code. No?
yes, in D-Wave, for example, so we run
Print
D-Wave.
it into the parameters.
Right. In D-Wave, there is a let's talk about D-Wave, right? So this would give you an example. So first, D-Wave is an adiabatic quantum computing. I'll explain in a moment what is it. In principle, it is equivalent to standard quantum computation. So in principle, there is a proof by Rita Aronov that the type of computation that D-Wave is capable of doing is mappable to a real quantum computer. So what is a quantum annealing? What is the idea there? That's the bread and butter of D-Wave. It's the adiabatic theorem. suppose I have a Hamiltonian with a parameter, and I change the parameter slow as function of time. Then we know that the eigenstate maps to an eigenstate if I change it slow enough. What's slow compared to the gap, right? The gap gives me delta E with this mappable to some time. And if if I do the protocol slow compared to the time scale corresponding to this delta E, then an eigenstate would stay an eigenstate. And so how do you use it to build a computer? You have your target Hamiltonian, you want to find the ground state of that. So you parameterize, you start from a trivial Hamiltonian. Usually this is the ferromagnet Hamiltonian. And you do this linear combination, and you change slowly lambda from 0 to 1. When lambda is equal to 0, you're at the ground state of the trivial Hamiltonian. You change lambda slow enough, and you get the ground state of the target Hamiltonian. That's very simple idea. What's slow? Well, you have to make sure that there is no gap, that the gap is large enough compared to the time, and of course the time, the company doesn't assure that there is no gap, that the gap is large enough, etc. And there are claims that difficult problem would map to problems where the gap vanishes, etc. But
there's no issue with degeneracy. Like if you have the target state, which is the ground state is degenerate, and the initial. So I mean, it's not a one-to-one.
So the probability of the ground state to be degenerate is very, very low.
No, but this is a glassy system, so it's not degenerate.
Right. So yes, but usually in this case, so these are great points, and we'll discuss them towards the end. For now, we'll say that usually if you find something which is close enough to the ground state, you're good enough. Okay. For most practical use, you don't really need this extra. To be really, really the ground state. If you're epsilon close to the ground state, you're probably epsilon good. How does it work? Well, it has qubits. These are superconducting flux loops, right? They are coupled through RF squeeze loops, and the Hamiltonian is something like that. So you have the A term, which is sigma x, right? And the B term, which are sigma z, right? And what you do is you change A and B as function of time. You start here with A being non-equal, A being large, and B equals 0. So you start at the ground state of this trivial Hamiltonian. You ramp A down and B up, and hopefully you get to the ground state of the Hamiltonian. Of course, you can control these GIJs, and you can even control that. That's not very useful. It's useful sometime. I'll maybe say a word. So that's what in principle this machine can do. Can you put any GIJ? Well, not really. So at the moment the system has 5,640 spins. That's quite a lot. This is the current situation of the machine I'm running. That's the machine in Germany. You see the red points, these are defects. So the orange points are nodes that are not working, and the red links are broken links. So that's what we have at the moment. And the structure is like that. You have a unit of 8 spins, which has this strange connectivity, and then they are somehow interconnected. Definitely not all to all. Roughly each spin is connected to 16 other spins, right? Now, if I give you a problem and you are able to map it to the Shelton-Kirkpatrick problem, usually this would result in a mean field of all-to-all connectivity. You cannot do that. What you often do is lump a few of them with a very strong coupling, and then think of it as a single spin, increasing the number of coupling you can have. Okay, so these are the specifications. Right, so each node is like that, and they have plenty of couplers, but not enough to really couple everyone to everyone. Right, it's somewhat limited, and a lot of the issues is this limitation because you cannot really map a problem directly here. You have to somehow embed it, and that gives you a cost. Yes.
Do you have any control on the couplers except for defects? Because it looks like this graph
Yes.
almost trivial.
No. Whenever you have a line, you can tune the GIJ in some range.
Okay.
Right? So basically, you can think of it from -1 to 1. So there is a limit to how strong you can generate them, but you can make them both positive and negative with some accuracy and resolutions.
The defects are not intended. They just
No,
it's
they
something
change as
broken.
function of time. Yeah. With time, they grow, and then they do maintenance. They suddenly, right? It's really, you can get it basically every day. So is this a real quantum computer? As I hint, well, does any quantum effect happen inside? Yes, these are flux qubits. Something quantum happens there. But is it a universal fault-tolerant quantum computer? Definitely no. No one claims it is, right? That's not the idea of D-Wave. People are not running D-Wave to crack the RSA. Not at the moment, probably not in the near future. That's not what they're all about. The main issue is, does it provide scalable quantum speedup for hard problems? Largely it's believed that the answer is no. So there is no specific problem that demonstrate quantum supremacy, that the scaling is much better than any classical system that we can have. But it's hard to compete with, it's hard to really compare with classical algorithms because the embedding issue and many other issues that I'll discuss in a moment. Nevertheless, it looks like a good solver in practice. So in many specific problems, this seems to be doing good. If you have a problem, if you're a company, you don't care much about physics, you care about, well, what's the best solution I can get? Sometimes this would give you a very good solution, better than we can get from our usual Kubo algorithms that we run on our computer.
Better in what sense?
Lower energy.
Either faster or lower energy. Usually it's the energy. So just I'll mention that why am I doing D-Wave? Part of the motivation, we wanted to run it as actually to do a relaxation experiment in statistical mechanics. It's coupled to a thermal bath, and we were able to measure, scale, rather the temperature, scale the coupling constant, measure equilibrium line, and try to measure relaxation. But pretty fast we understand that we want to understand the relaxation dynamics. They keep the time short enough such that the relaxation dynamics would not be relevant, so we are not doing the same. It's not really a tool for that, but since the students learned how to run the D-Wave and we invested a lot of time and effort in that, we start doing other things. There are many works that compare D-Wave to different classical algorithms. So you can find dozens of such papers. Here is an example. I'll show an example where D-Wave works best. So for example, there's no embedding issue. If you take a problem where you don't have to spend extra spin coupling them and think of them as a single spin to increase the number of links, then D-Wave is really doing good. We compare to algorithm with guarantee. So this was a collaboration with Danny Hermelin from Ben Gurion University. He and actually also Rami Pugach are not in physics but in engineering department. And they suggested a very interesting measure of how to compare. So we compare classical algorithm to D-Wave, and the comparison is based on result per dollar. So suppose I pay $1,000, I take the best solution I can get in Azure, so I run classical algorithm for this specific, my pointer is off, so for the specific, they found the problem that you can really embed directly in D-Wave.
It's on, but it doesn't switch the slides unless you plug in.
Okay, this would be great. So they found a class of problem where you can directly embed on the D-Wave graph, and they compare to their algorithm, which are the best known for this problem. And the comparison was, suppose I have 1,000, so yeah, they're engineers, suppose I have $1,000, what should I use? Yeah, this is dead. So that's the result. As you can see, D-Wave find for given price, D-Wave found lower energy, right? So the heuristic algorithms are better than the algorithms that have guarantees. So these are mathematical algorithms that have guarantees. The heuristic did better and D-Wave did even better. So at least for this class of problem, if you don't pay many overhead, etc., D-Wave seems to work quite well. Yes?
Just to understand, found the same solution but faster and less energy, or it's a different
No,
solution?
it's not the same solution. So
Different
you
solution.
see energy, I'm finding the ground state of Hamiltonian. I don't know what's the real ground state. The real ground state, no one is able to solve. So I take the distribution of energy I get from D-Wave. These are significantly lower than the two algorithms would compare. Yes.
At the time, I remember that Matthias Troyer claimed that
Yes.
he can do as good as D-Wave.
Yes, for other problems. So we met a very specific problem that, just because, and the interesting point with this problem is that there is no overhead. But still, largely, today I can say there are a lot of issues here. We'll see it in a moment. The main problem is how to compare apples to oranges. There are many problems in comparing D-Wave and also other analog computers. First, as I mentioned, there is embedding overhead. Usually, even in optics, the coupling is not all-to-all, and usually the problem you bring from computer science are all-to-all through the mapping. So you have to do some tricks, and these are usually something you pay a lot. There are many other implementation errors. I'll discuss this a lot. Basically now, if someone runs D-Wave and doesn't show me that he really knows how to run D-Wave, I don't trust the result, and I'll show you why in a moment. There are issues of what to compare, how do you compare, right? Most of the algorithms, the classical algorithm, if you run them longer, you get better and better results. So what do you compare, right? You have to somehow compare the clock of the D-Wave, the clock of the computer. It's not obvious how to do that. So what's the time to solution, etc. It's not, so in both cases, also in D-Wave, if you run more and more threads, you'll find more and more lower and lower energy. When do you stop? And also, what is a real difficult problem? I'll discuss this a bit later. So what we, and actually also others, are now suggesting is a different approach. Let's study the physics or the physical advantage directly of the web rather than trying to see how it solves a specific problem. So what is the idea? We understand that, okay, the coherence time of D-Wave is nanoseconds. You run for almost a millisecond. That's not the issue. That's not the benefit. What you can have is first tunneling and the adiabatic following. These are the two things D-Wave suggests. And so we can study these separately. For example, try to understand how good D-Wave is in tunneling, for example. And how can we do that? Let's measure them directly. Let's embed an exactly solvable model and measure the relevant properties directly. Let's see, well, D-Wave claims the idea is that you can tunnel under barrier and find the ground state. That's why it's better than simulated annealing. Let's measure how good it is at tunneling, right? So that's what we did. And how do you do that? You embed the 2D transfer field Ising model, right? The graph they present is sparse. Not everyone is connected to everyone, but you can do the 2D Ising transfer field Ising model. So this is the Hamiltonian we mapped. And it's known to be equivalent to the 3D Ising model. I usually do classical systems, and so in many of the calculations, actually I claim results that we calculate in the 3D Ising model. So you map this, and you check. The first thing that you do is you do sanity check. For example, check what is the critical temperature that you get, and does it agree with theory. Once you understand that, okay, you're good, then your mapping works well, you get the exactly result, the exact numbers that you know from the solutions, then you can do something like that. So we started in the wrong state, so we added a small magnetic field, an epsilon magnetic field. We started the wrong metastable and looked whether it would know how to tunnel to the real ground state. And since we can calculate the height of this barrier, because it's basically the 3D Ising model, we know everything about it, we know what's the height of the barrier and how it scales and everything we can really calculate. We can try to do this simulation and understand, okay, what are the capabilities of such a machine? Right, so that's the goal. We tried to do that, and then it took us more than a year of spending money on D-Wave. We didn't really pay because we won some grant for computer time, but it taught me that what we did before with the different models, to really run D-Wave, you have to work really hard in dealing with things that they swept under the rug and usually they don't care about. For example, magnetic leaks. If you have strong GIJ, you have systematic bias and you have to measure them and compensate for them. That's why the small magnetic field turned out to be, the local magnetic field, this HI, turned out to be useful. You have to, that's not something that someone tells you how to do. You want some gradient descent or something like that to really know that you don't have this bias. And this bias depends on your GIJ specifically, so it's not something you can plan in advance. You have systematic bias. Well, this you can map at least, but again, you have to do it yourself. No one gives you a map, and it changed after a few days. There are freeze-out problems. For us, since we measure the 2D Ising model, temperature fluctuation are horrible. Actually, we ended up doing the following. We use the spins that we cannot use for our experiment for the embedding of the 2D Ising model as a local thermometers, and we measure the distribution of temperature from these spins. The claimed value is roughly here, 15 millikelvin. That's the distribution of temperature that we measure, and we compensate for this temperature at every measurement. Right? So we actually, this is crucial. If you don't measure temperature at every instance, you don't get a reasonable result, right? There are other issues. You cannot really run long anneals because then we found out that there are memories effects. So somehow the spins, when you reinitiate the system, it remembers what was the last thing it measured. It's not really uncorrelated. It's a different measurement. So there are gazillions of such issues, and it took us a very long time to really be able to get to a place where we believe our results. Why do we believe our results? Well, because we can do things like that. We can calculate the critical exponent. We can find the critical temperature using the Binder cumulant for different plasticides. They cross exactly at the theoretical value. We get the real good agreement in all the critical exponent. We have a data collapse. So if you deal with all the many issues that probably if you are, I don't know, companies that pay D-Wave just to run your optimization, no one does for you. If you really work all that out, you can get to a place where you believe that, yes, what I run on my D-Wave is what I actually believe I run and it works. So after all this calibration, etc., it's hard kind of experimental work, but we don't really do the experiment. We just sit in front of the computer and run the machine that sits in Germany.
The solution is to cut it? I mean, if you run it again, you get the same solution?
No, so at the end of the day, you measure something, a single realization, and then you average over many realizations. So you have to do this average. Okay? So after we got to the point, yes?
Why do you average? Like, why not just choose the one that has the lowest energy?
Again, this is demonstrating that I can do the 2D Ising model where instead of changing the energy, I change the temperature, I change the coupling constant, right? I have to scale it based on the energy, etc. But For example, for the critical exponents, that's
No,
what you
but
do.
generally
No, the-
speaking, you would just
Yes.
choose the lowest energies.
Yes, but again, when you map, if you didn't really do something like that that proves that you can calibrate each node separately and it's roughly there, I wouldn't trust the result, because there are so many biases that if you don't deal with them, you're probably very off. So that's why I don't really trust it.
The biases are JIJ set specific. So if you now try, after solving all this,
You have
still,
yes.
I mean, so you never can solve
Yes.
a problem which you don't know the analytical solution at all.
Well, you can try to converge to something, yes, right? But yeah, it was really, luckily we didn't pay the way because we spent most of the computing time was calibrating. So the calibration is a huge part. Luckily, the spins that you are not used are often very useful for this calibration. But it's a real issue. You usually have to spend a lot of time in the calibration. What they sell you is, no, you just bring us a JIJ and we run. Forget it, it's not going to work. After you do that, you can try to see something like, okay, let's have this transverse field, right? If of course, if this is just the 2D XY, there is no tunneling here because that's an eigenstate, but if you add a small transverse field, you allow tunneling. This is now not the 2D, this would amount to like being the 3D Ising model, and you can actually measure what's the rate at which you tunnel, and as you can see, there is a sharp transition. We can calculate what the barrier height for this model at this transition. This is about 60 kBT barrier. So 60 kBT for the relevant temperature, that's probably tunneling. That's not, well, not probably, that's surely a tunneling. That's not thermal fluctuations. Okay? So, great. So we have these capabilities, and now we can try to, and now actually what we do is we try to understand what are the capabilities. So tunneling, we pretty much have a good picture of when the system can tunnel from one state to the other. The next thing is to work on the adiabatic following. Before doing that, here is a nice spin-off of that. Why not classical all the way? So this is an idea pushed by Toshiba and Fujitsu. The idea is that you want to find a minimum of such Hamiltonian. Well, quantum dynamics seems to be very powerful even without any coherence issues about. Why not lift it to classical Hamiltonian and try to use the classical adiabatic theorem. So the classical adiabatic theorem, you probably learned in mechanics, the 1D case, the n-dimensional case, surprisingly was proven by a mathematician only in the 70s. But it exists, and you can try to do the same. So you lift the Hamiltonian, start at low energy, and change it adiabatically. There were a few suggestions. That's basically how the Toshiba machine works. And they claim to do much better than simulated annealing or coherent Ising machine. They claim to do quite good of a job in doing so. And so let's do some wrap. So do analog computer really works? So here's a breaking news. It's not actually that breaking news. The date here is 2025, but it's on the archive a few years ago. It's a paper by Andrea Montanari, optimization of the Shannon-Kirkpatrick Hamiltonian, and let's see what he claimed. We consider the problem of maximizing. Okay, instead of minimizing, he's maximizing, but the same. Basically, our problem, in the language of statistical physics, this amounts to finding the ground set of the SK model. Basically, he says that for any epsilon larger than 0, he can find the solution or up to an epsilon. This converge to the probability converge to 1, it then goes to infinite limit, and the complexity is n squared. So he claims This is a very sophisticated message passing algorithm of Montanari that he can solve this problem at n squared. So what's the deal here? Does he say that p equal np? No, that's not what he's saying. But if you read carefully what he's saying, he says that all these analog computers are out. So let me try to explain what's the idea here. You have a rough energy landscape. So each Jij corresponds to some very complicated energy landscape. If you average over this Jij, which also like increasing your system size, you can look at the distribution of minima's energy. So you have here many minimas. Each one of them has its own energy, and they have a given distribution of energy. You care about this, right? And in the large n limit, what in the literature they usually call is complexity. You take the log of this distribution, 1 over n in the n goes to infinite, so this would be the large deviation. This is like an entropy, measuring the entropy of this. And usually you get a graph like that, right? What does it mean? You have a complexity which is positive, so you have exponentially common minima here. You have exponentially rare minima over there, so there are exponentially rare realization of Jijs where you'll have minima over there, and you have this which almost always, so up to exponential realization of Jij, almost always this would be the ground state. That's actually for the Kirkpatrick, that's given by the Parisi formula. And what Montanari, the algorithm, find, and physical devices, that's a conjecture, but I'm pretty sure about it. What physical devices found is the same as what Montanari finds. And to some extent, you can even understand why they do something not that far from what Montanari is doing. So what they find is here. But this is not a difficult problem. The fact that the problem is NP-complete doesn't imply that for every Jij it's difficult. For example, I can take the ferromagnet. I know to find the ground state of a ferromagnet very easily. It's not a difficult problem. There are exponentially rare problems in the Jij. That's exactly the point that Eli brought before. Most of the Jij turns out to be easy problems. There are exponentially rare realizations which are really NP-complete and would be extremely difficult. So saying that something is NP-complete means that the worst case scenario is really, really difficult. It does not mean that the average case. And what physical devices are good at, and all the measures are usually on the average device. And I think that in that sense, they are pretty much equivalent to these algorithms, and they are not really able to solve these hard problems. They are hard to find these hard problems. So at least.
So do we know how to know whether the problem is hard? I mean, traveling salesman problems. I give you a scheduling problem, and and you can't. Can you tell me? Well, oh, this one's an easy one, and I can do this one.
No, but I can tell you that if you choose them on random, they will be easy. There are difficult problems, but they are not. It's not obvious that they are. So you don't get them by random. Okay. With that, let me thank my team. Gianluca worked on the D-Wave with Ran Jacobi. Igor and Bernard worked on the laser with Nir. We also had some how to cross separatrix with Ro'i. We had a lot of help from Ofer Zaitouni and Eliran Sabag that correct us on the math side. And the experiment, not the D-Wave, but the experiment on lasers are by Nir Davidson. So that's how I'm related to this issue. And of course, funding.
Thank you very much, Oren, for this very interesting talk on a somewhat disappointing issue. I think we had quite a few questions during the talk, but maybe a few fast ones. Yes, please.
Do you do anything special to avoid the metastable states?
What, in D-Wave?
Yeah, like the adiabatic protocol that you're talking about?
So actually, we start deliberately on the metastable state, wanting to measure how fast you tunnel out. So that's exactly what we use. We use the model where we know the metastable state, we know the energy difference, we know what's the height of the barrier, so we can calculate everything. That's exactly the approach we. Of course, if you give me a general Jij, I have no clue what the barrier height is. But you can estimate what's the statistics of the height of the barrier, what's the statistics of the energy difference, etc. Yes, Eli.
So everyone is using this Gaussian distribution for Jij. Now, if you want rarer landscapes, I would say you should use. Okay, 1 Stopian Gaussian would be exponential decay, and then you'll see more rare events, and they will be more typical, at least at some temperatures or something like that. So why is everyone fascinated with these Gaussians?
Because you can solve it. So to some extent, now forgive me if you don't understand, to some extent, what Montanari showed is that full replicable symmetry breaking is difficult. 1 RSB is already complicated, and you're right. So if I give you a problem with 1 RSB, it will be way more difficult to find its ground state compared to full. So yes, there are ensembles that would be more difficult. So at least Montanari's algorithm are not going to solve it, and there are not known algorithms that would solve it. Yes, so replacing the statistics is a good idea.
But going back to the air conditions, let's be practical. What is the right distribution? Is it?
It's hard to believe that this would be Gaussian. Again, we use Gaussian basically because we know how to integrate Gaussian variables. That's the main reason, right? In the replica trick, you can integrate over the probability of Jij's. That's the main reason you do Gaussian.
So after you started solving, can you tell at the end of the solution how close you are to the real minima, or how complicated the problem was? Can you tell, like, I solved it, okay, I can see this problem was actually
very far from
the solution.
In practice, no. Okay. You can tell how far you are from the Parisi solution, but not more than that. Right, Parisi solution is very rare case where we actually know what in most realization the minimum should correspond. But we have it to very few ensembles.
Okay, at this point, let's thank the speaker again. See you again next week. Okay.